So good morning all of you. So today we will discuss about the transformers. Transformer is an AC device. So transformer operates only on AC. It is an alternating current device. So the name itself indicates transformer. Transformer means trans means change, former means previous values. Transformer means transformer changes previous values of voltage and current to new values of voltage and current. So that means transformer changes current and voltage values to a new values. So that means maybe increase the voltage or it may be decrease the voltage levels. Simultaneously, current values also changes. Always remember, transformer is a constant power device. Transformer is a constant power device. It does not increase the power levels, change the voltage and current levels simultaneously. If it increases the voltage level, then the transformer is called step-up transformer. Suppose if you give a 230 volts input voltage, then you get 440 volts output voltage, then the transformer is called step-up transformer. So that means voltage level increases. Simultaneously, current levels decreases. Voltage levels increases, current level decreases. So power is always constant. Voltage into current, it is a power. Power is always constant. So in a transformer is a constant power device. We are not able to increase the power levels with the help of a transformer. If you want more power, you must install a generator, not a transformer. Transformer changes voltage levels. Transformer changes voltage levels and simultaneously current levels. It does not increase the power levels. So that is the transformer. Trans means change, former means previous. Previous means input values. So transformer changes input values of voltage and current to new values. Okay. So need of the transformer. So what is the need of the transformer? Generally, power is generated in remote areas, so far from the load centers. So if you want to transmit power from long distances, so for lower values of voltages, currents are high to maintain constant power. Current values are high. So if currents are high, losses is also high. Because I square or current value is more means copper losses is more. Because copper losses depends upon current. That is I square R losses. If current values are very high, so copper loss is more. Copper loss more means efficiency of the transmission system is low. So that if efficiency of the transmission system is low means total system efficiency decreases. So that means per unit cost of power increases. So to reduce that one, you must decrease the current values to transmit the power to long distances. Transmit the power long distances, we decrease the current levels. Simultaneously, we increase the voltage levels with the help of a transformer. So it means with the help of a transformer, we increase the voltage levels. Simultaneously, we decrease the current levels. Therefore, current levels decrease means copper losses decreases. Copper losses decrease means the efficiency of the total system increases. Efficiency of the total system increases means per unit cost of power decreases. So that is more economical. So for that purpose, we use transformers. So see here, so here power is generated at this point. Power is generated at this point. See this diagram. Power is generated at the generating stations. Power is generated at the generating stations with the help of a generators. Power is generated. The generated power is generally in between the 11 kV to 11 kV kilovolts voltage levels. 11 kV to 22 kV. In our India, power is generated in between to 11 kV to 22 kV. So the generated voltage values from 11 kV to 22 kV, maybe 11 kV, 18 kV, or 22 kV, or 21 kV. That voltage levels are increased with the help of a transformer. See, this is a generating transformer. So this is a transformer. This is a transformer. So transformer. So this generating voltage levels are increased to that is 138 or 230 or 235 or 500 volts or 765 kV. So this that means this voltage levels from 11 kV to 22 kV voltage levels are increased to new value of voltages, that is 115, 138, 230, 345, 500 or 765 kV transmission voltages. So these are the transmission voltage. Depending upon the distance transmitted, power need to transmitted, the voltage levels are determined. If you want to transmit over 60 kilometers or 100 kilometers, we step up the voltage up to 132 kV. If you want to transmit 200 kilometers, 230 kV. 300 kilometers, 400 kV. 600 kilometers, 500 kV. So 1000 kilometers, 765 kV. In that manner, voltage levels are increased with the help of the transformer. So with the help of this transformer, we increase the voltage levels to a transmitted voltage, and then after so suppose this is a transmission line. This is a transmission line. This end is called the sending end of the transmission line. This end is called the receiving end of the transmission line. Sending end. This end is called the sending end of the transmission line. Sending end. So this end is called the receiving end. Receiving end. Sending end and the receiving end. So here we place another transformer at receiving end. So this transformer decreases the voltage levels to distribution value. Distribution value, that is new value, so 26 kV or 69 kV or 13 kV or 4 kV or and suppose this is not existing in India. This voltage is that is 11 kV, 11 kV or 440 volts, 440 volts or 230 volts, 440 volts or 230 volts single phase supply, 230 volts, 440 volts is for three phase supply. So that means we reduce the voltage levels to customers' usable values. Usable values means lower voltages, because higher voltage we never use higher voltage, that is 400 kV or 200 kV or 132 kV we never use. We use small values of voltage, that is 230 volts or 400 volts or like that. So for that purpose we use transformers. So transformer cannot increase the power levels. Transformer only changes the voltage and current values to a new values, voltage and current values to a new values. So that is the main purpose of the transformer. That is the main purpose of the transformer. So for that purpose we use a transformer. So transformer is an AC device. It works on Faraday's laws of electromagnetic induction, that is the mutual induction. Mutual induction principle. That is same Faraday's laws of electromagnetic induction. DC machines also operates on same principle. So transformer is also operates on the same principle. So that is the main purpose of the transformer. Purpose of the transformer is it changes the voltage and current levels. Voltage and current levels. It may be increases or it may be decreases. If voltage levels are increases, that is called step up transformer. If current voltage levels are decreases, it is called step down transformer. Step down transformer. So you see, what is the need of transformers? In most cases, appliances are manufactured to work under some specific voltages. Suppose all household devices are operated on 230 volts. Transformers are used to adjust the voltage to a proper level. The main purpose of the transformers is to adjust the voltage levels to a proper level, usable values. Or in case of transmission, the voltage levels are increases. In case of distribution, the voltage levels are decreases. We have mainly three systems in our power systems. In our power system, we have three main systems. Three. One is generation. One is the generation C. One is the generation. Second one is the transmission. So generation, transmission, and distribution. So first one, generation, transmission, and distribution. We have made three major parts in our power system. Three major parts in our power system. So first part, generation. Power is generated, power is transmitted, power is distributed. Three main parts. One 2 and 3. 1, 2 and 3 generation, transmission and distribution. So for utilization, distribution and utilization. The distribution and utilization comes under the third category. First category generation, second category transmission, third category distribution. So the transformers are basic component of transmission of electricity. So we have transformers, so that's why we are transmitting power in long distance. Without transformers, we are not able to transmit the power to long distances because the losses increases, the system efficiency decreases. So we have transformers, therefore we transmit the power to long distances. Transformers Transformer is used to increase the voltage at power generating stations. So that is generating stations power is increased with the help of sorry voltage levels are increased with the help of transformers. That is called a step up transformer. That is called a step up transformer and used to decrease the voltage step down transformer for household purpose. Household purpose means utilization purpose. So we are not able to use the voltage at 400 kV or 132 kV. We are able to increase use the voltage values at 230 volts or 440 volts only. Single phase 230 or 440. So that's why we need transformers to transmit the power by step upping and step down or use the household purposes. By increasing the voltage, loss of electricity in transmission is decreases. So losses are decreases by increasing the voltage values. I already explained. See, a transformer is a device that change AC electrical power at one voltage level to AC electric power at another voltage level through action of magnetic field. So transformer changes the voltage levels only. It cannot increase the power levels. Change the voltage levels to one value to another value. There are two or more stationary electric circuits that are coupled magnetically. There are two or more electrical circuits that are magnetically coupled. That I will explain later. It involves interchange of electric energy between the two more electric systems. So transformer is a coupling device. It interconnects the two or more energy electrical systems. So transformers provide much need capability of changing the voltage and current levels simultaneously. So it changes current levels and voltage levels. They are used to step up the generating voltage to an appropriate voltage levels for power transfer purpose. Stepping down the transmitted voltage at various levels for distribution and power utilization. Step up the voltage at generating stations and step down the voltage at distribution and utilization purposes. So transformer is a static device. That means there is no rotating parts in transformer. There is no rotating part. It is static. Static means stationary. Transformer electrical energy it transfers electrical energy from one part of electrical or electronic circuit to other part of the circuit without change of frequency. If you give some value of frequency, output it gives the same frequency output. That means input equal to 50 Hz, output is also 50 Hz frequency. It works on Faraday's laws of electromagnetic induction. So here I will show one video for you. Here understand the principle of operation of the just a minute.
relay, temperature thermometer, and the dehydrator breather. So let's get stuck right in, and we can start by looking at the heart of the transformer, which is the transformer core. So here we have a 3D model of a transformer core.
So this is the
We'll do a little spin.
Transformer core, basic supporting structure core of transformer.
As you can see, this core has 3 limbs. So these 3 limbs indicate to us that this is a 3-phase transformer. The top and the bottom of the transformer core are known as the yoke, and these 3 pieces in the middle are known as the limbs. So each limb correlates to one phase of the transformer. The core itself is clamped together, usually using adhesive or some straps. If we look on the bottom here, we can actually see there are 3 straps. It's these items here.
So this is the basic core of the transformer.
And you'll see there's also straps on the other side. 1, 2, 3. So the transformer core is clamped together, and the reason it's clamped together is because the core is not one order that we can get a...
So this is the basic core. Here we explain the principle of the operation. So in transformer we have 2 coils. So this coil is called primary coil. So this is the primary coil of the transformer. Coil 1, this is nothing but winding. This simple wiring, just simple copper wire. This is simple copper wire. Primary winding. So this is the secondary winding. Secondary winding. So we have 2 coils, coil 1 and coil 2. So that is the primary coil and secondary coil. So primary winding and secondary winding. Primary winding having NP turns, secondary winding having NS turns. So here we have input voltage Vp, output voltage Vs, input current Ip, output current Is, secondary current, primary current, primary voltage, secondary. So we have 2 coils, primary coil and secondary coil. We give input voltage to primary coil. So output is connected to load. Output here we connect to load, electrical load. So this is the basic transformer circuit.
High magnetic field density or magnetic flux. So that's what the core is doing. So we've got our limbs in order that we can get a high magnetic field.
See, suppose an alternating current is given to this primary coil, alternating current, AC supply. If we give AC supply to this primary coil, AC supply to this primary coil, an alternating flux will set up. An alternating flux will set up. So because every current carrying conductor produces magnetic field around the conductor. If we give AC supply to this primary coil, because transformer is an AC device, operates on AC only. If we give AC supply to this primary coil, so an alternating flux similar to alternating supply voltage, an alternating current will flow in the primary coil because it's a closed coil. So voltage gives current, that current produces flux. That current produces a flux. So this is an alternating flux. This is an alternating flux. So the alternating flux produced by the primary coil, passes through this core because core allows magnetic flux. The core provides path for magnetic flux. Core provides path for magnetic flux. So this flux produced by the primary coil passes through this magnetic core and links this secondary coil. So this is the nothing but this is the secondary coil. This is the secondary coil. An EMF will be induced in the secondary coil according to Faraday's laws. According to Faraday's laws, when flux linking with the conductor changes, because this flux is an alternating flux. Alternating flux means having positive and negative cycles. Positive and negative cycles. So the alternating flux links with the secondary coil. An EMF will be induced on secondary coil. So that EMF circulates the current when secondary circuit is closed. When a secondary is connected to load, electrical load, suppose in this manner, electrical load is connected in secondary circuit. So the EMF induced in the secondary coil circulates the current. In this manner, power is transferred from primary to secondary in a transformer. There is no direct electrical connection between the primary coil and secondary coil. There is no direct electrical connection between the primary and secondary coils in transformers. So we give AC supply, then we obtain the same AC supply. So depending upon the number of turns on primary and secondary, primary turns NP and secondary turns NS. If secondary having more number of turns, then the transformer is called step-up transformer. If secondary turns less than the primary turns, then the transformer is called step-down transformer. So step-up NP, NS is greater than NP, NS is greater than NP. That means secondary turns is more, step-up. Secondary turns is less, step-down transformer. So this is the basic principle of a transformer.
In order that we can get a high magnetic field density.
So this is the basic core of the transformer, core structure. Core, you know that core provides the support for the winding. Core provides support for the coils. Coils are wounded. Copper winding is made on the core. Wound on the core.
That much. The only notable transformer.
So this is the wounded. So that means we see here, this is the core structure. Core, this is the core. In this core, we provide insulation and then the winding. Winding is provided on the insulation. Core, insulation, and winding. So this is the winding coils, copper coils.
This is a type of. Okay, the top voltage windings are going to be installed closest to the core of the transformer. So they're going to be wrapped around.
See. So primary and secondary windings. So we have two windings in transformer, primary winding and secondary winding. So this is the basic core. So we have two types of core construction in transformer. Core transformers, core type transformer and shell type transformer. So see the difference between the core type and shell type. So in core type transformer, just we have one window. So this is one window in core type. In shell type transformer, we have two windows. So this is the one window, this is the second window in shell type. So in shell type transformer, winding is surrounded by the core. Winding is surrounded by the core in shell type. So in core type transformer, core is surrounded by the winding. Core is surrounded by the. That is the basic difference between the core type and the shell type. So this is the core type transformer. This is the shell type transformer. See, the windings are placed in this manner. Primary and secondary windings are placed in this manner. So in a core type transformer, first this part and this part is one winding, and then insulation and second winding.
Very close, should I say, to the core. Immediately after the low voltage windings, we're going to have high voltage windings. So we've got our primary and secondary windings installed, and if we push the play button, we can actually see them coming down onto the core. Here come our clamps. Here comes some sort of insulator, most likely.
This insulation.
And here comes some windings. And the HV windings that go on the outside. Once that's all assembled, it's going to look a lot like this. And we can see by looking at the back what type of wiring configuration that transformer has. So they're going to be wrapped of limbs.
See, first core.
Remember, one limb is one phase, so this is a three-phase transformer.
So this is the windings.
And within this group, we're going to have low voltage windings and high voltage windings. The low voltage windings are going to be installed closest to the core. So they're going to be wrapped around, or very close, should I say, to the core.
High voltage windings.
Immediately after the low voltage windings, we're going to have high voltage windings. So we've got our primary and secondary windings installed, and if we push the play button, we can actually see them coming down onto the core. Here come our clamps. Here comes some sort of insulator, most likely. And here comes some windings and the HV windings that go on the outside. Once that's all that we've got.
So this is the outer supporting structure of the transformer.
That's these four thick ones here. The reason they are the low voltage bushings, or the reason that you can tell, is because the connections are very large. The reason they're large is because the voltage is low and the current is high. So that's a giveaway that the low voltage bushings are these four here. And we can see there is our transformer core again, 3 limbs, that's 3 phase. We've got the 2 yokes, one at the bottom, one at the top. And we have our bushings. And all of that can be assembled again to complete the hermetic type transformer. So essentially, the hermetic type transformer is a dry type transformer, but with a box around it or a casing that is full with a insulating liquid. Now, this insulating liquid is typically mineral oil. About 95% of the time it's going to be mineral oil. And the whole thing sits in a bath of mineral oil. The reason it's called hermetic is because it is totally isolated from the atmosphere.
To know what is a transformer, why the transformer is called the static device, how the transformer transmit the power at the same frequency, what is the working principle of transformer, self and mutual induction phenomena on transformer, and how the transformer work. So friends, let's get started. First of all, understand what is a transformer. The transformer is a static device which transfers the alternating electrical power from one circuit to another at the same frequency. Now here two questions arises in your mind. First one is that why it is called the static device, and second one is that how it transfers the power at the same frequency. Now first understand why it is called the static device. The transformer has no moving part, means like you can see in the induction motor there is a rotating magnetic field, stator, rotor, and also the torque generated in that motor, it is also rotating in nature. So that machine has rotating part for completing their process. But in transformer, complete process of transferring the power can done without any rotating part. Transformer simply has no rotating part, and the complete transfer of power can be done through their static part. This is the reason, friends, we call the transformer a static device. Now how transformer transfer the power at same frequency? Here you can see in this image the transformer consists two electrical circuit and one magnetic circuit. Okay, so these two electrical circuit are interconnected by one common magnetic circuit. By the help of this magnetic circuit, the transformer are capable of transferring the power at the same frequency. Working principle of transformer. The transformer work on the principle of electromagnetic induction. The electromagnetic induction phenomena says if we supply the alternating current across the coil, then alternating flux induces across the coil. The magnitude of the flux is directly proportional to the current induces in the coil. Also, the direction of flux is depend on the direction of the current. By the help of the right hand grip rule, we can determine the direction of the current. The right hand grip rule says if we hold our right hand finger like this, then the curls of the finger shows the direction of the current, while the direction of flux is given by the thumb. Now here we can say because of the alternating current, the alternating magnetic flux induces across the conductor. This flux induces the EMF across their coils. So here we can say this induced EMF is the effect, and it is caused because of the alternating current. Now according to Lenge's law, the causes always oppose the effect. Here effect is the alternating EMF that induces in the coil, and the cause is the alternating current that we supply to the coil. So according to Lenge's law, this EMF always opposes the supply voltage. Here in this case, the polarity of the induced EMF is opposite to the supply polarity, and hence we can say this EMF opposes the supply voltage. Now consider we are placing one more coil near to the alternating flux of the first coil. So according to Faraday law of electromagnetic induction, the EMF induces in the coil. Because of this EMF, the current of very small magnitude start flowing through the coil. The magnitude of current is small because there is an air gap between the coil and the air gap has very high reluctance. Because of the high reluctance air gap, the small magnitude of alternating flux links with the secondary coil and hence a very small magnitude of current induces in the coil. Now, for inducing the large magnitude of current in the secondary coil, we need a low reluctance path between the coil. So here in case of transformer we are using the steel. Friends, the steel provides the flux a very low reluctance path, and because of this low reluctance path the whole of the magnetic flux that induces in the first winding is induces to the secondary winding, and the equal magnitude of current start flowing in the secondary winding of the coil. Working of transformer. The transformer has mainly two main parts. These are the windings of the transformer and the core of the transformer. The core of the transformer is made by laminated silicon steel. This laminated silicon steel provides the very low reluctance path to the magnetic flux, and that's why we are using it for making the core of the transformer. Okay, here we have two separate windings. The first one is the primary winding of the transformer and the second one is the secondary winding. The winding through which we supply the input to the transformer, that winding is called the primary winding of the transformer, and the transformer through which the load is connected, that winding is called the secondary winding of the transformer. Here what happened, when we give the alternating supply to the primary winding of the transformer, then one alternating current start flowing through that winding. Because of this current, the flux induces in the winding. This flux induces one EMF in the winding. Now how this flux induces the EMF in the winding? This happens because of the self-induction phenomena. The self-induction phenomena says if alternating current flow through any winding, then EMF induces in the winding. So according to self-induction phenomena, one EMF induces in the primary winding of the transformer. Now we can say that this EMF is the effect of the supply voltage, means this EMF is the effect and it is caused because of the supply voltage. Now here comes the Lange's law. The Lange's law says the cause always opposes the effect. So here the EMF induces in the winding because of the supply voltage, and hence we can say that this EMF opposes the supply voltage. The polarity of the induced EMF is opposite to that of the supply voltage. Now the flux that induces in the primary winding of the transformer, that flux link with the secondary winding of the transformer. This happened because of the mutual induction phenomena. Now here, what is mutual induction? The mutual induction phenomena says when we place any coil near to the alternating current carrying coil, then the flux that induces in the alternating current carrying coil, that flux links with the secondary coil too, and because of this flux linking, one EMF induces in that coil. The same phenomena happen in the transformer. So because of this mutual induction phenomena, the alternating flux of primary winding link with the secondary winding of the transformer. Because of this flux linking, E1 EMF induces in that coil too. Okay, so this coil, this EMF is also opposite in polarity because it induces because of the supply voltage. Okay, now because of this EMF, one alternating current starts flowing in the secondary winding of the transformer. Here the magnitude of the secondary current is almost same to that of the primary winding of the transformer. This happened because we provide the very low reluctance path between these two windings. We using here steel, and steel has very low reluctance path. Because of that path, whole of the flux that link in the primary winding of the transformer, that flux is completely linked with the secondary winding of the transformer. Ideally, we can say there is no loss between these two windings, but practically few losses occur in that winding too. This is all for today, guys. I hope you like my video. For detailed study about the topic, you may refer my official website, which is thecircuitglobe.com. Here you can see I explain
is also in electrical form. Also, the input and output both are in alternating form. Primarily, transformers are used to change level of voltage and current. For example, in case of step-down transformer, the input high voltage is transformed to a low voltage, whereas the magnitude of current is increases because input and output power has to be remain same. Working of a transformer can be understood by taking a simple example of a small piece of wire carrying current when it is connected to a battery. As a result, a magnetic flux gets set up around the conductor. If another piece of wire comes in the vicinity of this flux, an electromotive force is get induced in the conductor, which we can see here form deflection in needle of a galvanometer. But after some time, deflection becomes zero. Because both conductors are stationary, means there is no relative movement between them. This is known as dynamically induced EMF. Further, we can also experience that EMF is again induced in the second conductor when we remove battery. This is because of reduction in flux density around the first conductor, and the second conductor try to oppose this change in flux as per Faraday's law of electromagnetic induction. The magnitude of EMF induced is given by E2 is directly proportional to d phi by dt. This electromagnetic coupling between the two conductors can be improved by two methods. Number 1. By using coil on both sides instead of using single wire, this results in increase of flux. Number 2. By using a magnetic core between the coils, which gives low reluctance path to the flux and improve magnetic coupling between the coils. As you can see here, in this case, coil of left side, or we can call it primary coil, has lesser number of turns than the coil on right side, or we can call it secondary coil. And the transformer is called as step-up transformer. In this case, voltage which induced on secondary coil V out is higher than the voltage which is applied V in on the primary coil, whereas the current get reduced as the power has to remain constant. Similarly, when primary coil has more number of turns than the number of turns in secondary coil, the transformer is called as a step-down transformer, and the voltage induced on the secondary side, V out, is less than the applied voltage Vn on primary side. The core which is practically used in a transformer is actually not a solid core. It is made
up. Next discussion we will meet tomorrow because next class teacher is waiting. So I will leave the class now. We will meet tomorrow. Thank you.
of number of